Hola, chaps. Let's learn.
Hola, chaps. Mr. Turek here. This is for aerospace engineering. You guys are having lots of fun learning how to do trusses, so I thought I would try to do another example for you. So here I've created one, and I'm using two squares on the graph paper to represent 1 meter. So we've got A at the origin where there's a fixed pivot. Point B is 2 meters to the right of A. Point C is an additional 5 meters to the right of point B, and that's where the roller is located. And then 5 units up, 1, 2, 3, 4 units up is point D, and it's at the top of this point that I'm pushing down with a load of 100 newtons. Great. So analyze it completely. Figure out all the reaction forces and all the compressions and tensions throughout. Here we go. First, for the reaction forces, the philosophy is the sum of all the forces in the vertical direction have to add up to 0. So if I'm pushing down on it with 100 newtons, I must be pushing up on it with a total of 100 newtons at points A and at point C. But how do you divvy them up? To calculate the ratio of who gets how much, you should really be thinking in terms of torque or moment, choosing A to be the axis of rotation. And the height here doesn't matter. So I've redrawn this, showing how I would approach the reaction force calculation. I would put my axis of rotation at point A, the load applied at 2 meters, and a reaction torque or moment applied at 7 meters from the axis of rotation. So moment is the distance from the axis of rotation to the point of application of the force, of course, times the force times the sine of the angle between them. Now I slid the load along its line of action down to point B and drew this as just a simple straight line because that's all we need to think of it as. And the angle is now negative 90 degrees, and the sine of negative 90 degrees is -1. So the moment caused by the load acting at point D is equivalent to negative 200 Newton meters. That is the torque, I would call it, or moment, about point A caused by the load applied at point D. Now, sure, there's a reaction force upward at point A, but it can't contribute to the torque because the distance from the axis to the load that's being applied at A is 0. And so therefore the moment is 0. There's no twisting force. So to cancel this 200 Newton meters of positive or clockwise torque, there has to be a reaction force at point C to cancel this out. So the distance from the axis of rotation to point C is 7 meters, and the force here, reaction force at point C in the y direction, would be positive 200 Newton meters divided by 7 meters. Yeah, too bad I didn't pick nice round numbers, but I just randomly made this up, and I end up with 28.6 newtons is the upward push at point C, the reaction force at point C, to cancel out the torque caused by the load being applied at point D. Great. Well, now you should be able to do the last part that says the sum of all the forces in the vertical direction have to add up to 0. I have a load of 100 newtons going downwards. I have an upward reaction force of 28.6 newtons applied at point C. Therefore, at point A, the only other place where you can have a reaction force being applied, it's the difference, 100 newtons minus 28.6 newtons, and I just calculated that, and I get a result of 71.4 newtons is the reaction force at point A in the vertical direction. Now I kind of am learning from my mistakes, and so I would tell you that there is no horizontal reaction force in this problem. And we're now ready to go inside this problem. Okay, so I've taken a moment and I've redrawn the sketch, focusing just on vertex C. So we don't care about A right now. We don't care about the load at D. What's going on is that we've calculated that the reaction force at point C caused by the roller is 28.6 newtons, that it's 5 meters horizontally to get to point B, and it's 4 meters vertically to get to point D. These two truss members are the only forces acting on C that can cancel out the 28.6 Newton of the roller pushing up on point C. So BC can only push in the horizontal direction or pull in the horizontal direction. These truss members can only pull or push in the direction that they are drawn. So what can BC do to cancel out this 28.6 newtons? The answer is nothing. It can't do anything because it's perpendicular to this vertical force. Therefore, you have to look at DC, this truss member, to analyze how can it cancel out this upward force at point C. And the answer should kind of become apparent to you that D must be pushing down on point C. It's got to be canceling that out with a vertical component equal to 28.6 newtons. So you may have noticed that I haven't bothered calculating any angles on any of these examples. I've been cheating and taking advantage that I've always been drawing these things on graph paper and using the scale of the graph paper to very rapidly calculate the ratio of one leg to another leg, or use Pythagorean's theorem to calculate the magnitude of the hypotenuse. So I don't I don't know what the angle is on this one, but I can tell you that the vertical leg on this truss member is 4/5 of the horizontal leg component of this truss member. And by similar triangles, since it's going to be the very same angle for the forces involved, it's going to be the same ratio of horizontal to vertical forces in this situation. So if 4 meters of distance corresponds to a vertical force of 28.6 newtons, then the horizontal force of 5 meters must be 5 force of 28.6 newtons. So 5 force, you know, is 1.25. And if I type this in correctly, I'm ending up with 35.8, I'm going to call it newtons, is the, I should write that down someplace, right? So that is what DC is applying at point C. So DC has to have a vertical component, and I know I should do this to scale this right time, right? So 10, 20, 28, let's say it's like that. It's got to be pushing down at point C with a force of 28.6 newtons to cancel the upward push of the roller on point C. But the side effect is because it's at this diagonal, for every 4 newtons that it pushes vertically, it has to push horizontally with 5 newtons. And that ratio means it's really going 10, 20, 35. It's really pushing to the right with 35.8 newtons of force. And so now what I'm going to do, because, we don't want to stop here, we want to calculate what is the tension or compression in this member. So if a member is under tension, it's being pulled apart, and that means you could replace that stiff truss with a rope and it will still do its job. So ask yourself, if D is pushing on C, pushing, Could I replace this truss with a rope, and would it continue to push on C? No, the rope is just going to coil up. So this must be, instead of being under tension, this must be under compression. So I know we use letter C to represent this vertex, but we also use letter C to represent compression. And I would now fire up my calculator and calculate the square root of 35 point, let's call it 8 squared plus 28.6 squared, and I get 45.8 newtons. So member DC, if I were going to write it, is under compression in the amount of 45.8 newtons. There, I figured something out. And you should play Sudoku a bunch of times. Then you'll learn to enjoy this more as well. So I have just analyzed point C in terms of truss D, DC. How did I figure it out? First, I had to have the correct reaction force. The roller is pushing upward at point C. If I drop back to this diagram, the original diagram says this roller has to be pushing up to cancel the 100 Newton load that's creating a moment about point A. So that was this drawing. And 2 meters times negative 100 newtons must cancel 7 meters times 28.6 newtons. So that's how I got the reaction force at point C. Here, I redrew it, focusing just on point C and the two trusses connecting to it. I drew the reaction force of the roller pushing up at 28.6 newtons at point C, and realized that truss BC can't do anything to cancel it because it's purely horizontal. So diagonal truss DC must have a vertical component downward of 28.6 newtons. The side effect, because it's on a ratio of 4 vertical to every 5 horizontal, the side effect is not only is it pushing down, but it must be pushing to the right with a magnitude of 35.8 newtons. And by Pythagorean's theorem, that means member DC is acting under compression with a magnitude of 45.8 newtons. Great. Right away, you should be able to calculate what is the tension or compression in truss BC. Okay, go ahead, pause this, write it down. I'm not going to pause. So the vertical components are canceled between the roller pushing up and the vertical component of DC pushing down. The side effect of this diagonal truss is that it's pushing C to the right with a magnitude of 35.8 newtons. B is the only truss member left acting on point C, and its job must be to cancel out that 35.8 newtons that D is pushing C to the right with. So I would say 35.8 newtons is the magnitude of the pull of point B on point C. And I could replace a pull with a rope instead of using a solid substance. So this one is under tension. And I used to color code my truss structures whenever I analyze them. I used to always use blue once I figured out it was under tension, and red for compression, because after all, as a teacher, I always have the red pen of death. And I also added arrows. I think I used to do outward pointing arrows for compression and inward pointing arrows for tension. But I would understand it if you find that very confusing and you don't attempt to adopt that. However, you can still color code this. And so you could use a red marker for something that's under compression, a blue marker for something that's under tension, and we've analyzed 2 of the truss members so far. Looking at our original problem, what would you do next? Take a moment and figure that out while I set up my own decision. All right, my choice was, since it's pretty easy to do this one, I decided to analyze truss AB. So here is a drawing just showing the trusses that are touching B. Keep in mind that the sum of all the forces in the vertical direction have to add up to 0. The sum of all the forces in the horizontal direction have to add up to 0. And what we just established is that C is pulling B to the right with a magnitude of 35.8 newtons. Now, D is vertical, C is horizontal, A is horizontal. So what can D do to cancel out 35.8 newtons of horizontal force? Nothing. It can't do anything because forces in one direction are independent of forces in a perpendicular direction. So D is out of the picture. Maybe I shouldn't have even drawn it. What's left is truss AB, member AB, and its job has to be to cancel out the 35.8 newtons of pull that C is exerting on B. So therefore, that makes this thing pretty easy to figure out, relatively speaking. A must be pulling B to the left with a force of magnitude 35.8 newtons. And since it's pulling it, I could replace this stiff member with a rope and it would still do its job. So this is under tension. It shouldn't surprise you too much to discover that B is being pulled to the left by A and it's being pulled to the right by C. They cancel out. So the 35.8 newtons of C pulling B to the right is canceled by A pulling B to the left. Therefore, tension AB must be 35.8 newtons. So we've made a lot of progress. We've established what the reaction force is. You always have to begin by calculating the reaction forces first. And we did that by making the torques 0 about point A. And by the way, you could have chosen C as your axis of rotation instead. In that situation, you would have had 5 meters times 100 newtons to be canceled by 7 meters times the reaction force at A. And sure enough, I'm confident that it would have worked out to 71.4 newtons. And by subtraction from 100 newtons, that would make this thing 28.6 newtons. So you could have chosen your axis rotation at either the roller or the pivot point, and it would still give the correct results. We have figured out the tension of AB, most recently, the tension of BC, the compression of DC, and so now we have really 2 members left to analyze, BD and AD. And I think I'll start with BD because that one should be almost obvious to you on this drawing. D is either pulling B up or it is pushing B down. Which one do you think it's doing this time around? I know, you should have paused and then answered to yourself. However, think of it this way. The net force in the vertical direction on B is 0. And there's only one truss that's vertical. That's D. So in this situation, if D were pulling up on B, there's no force to cancel it. If it were pushing down on B, there's no force to cancel that. Therefore, there is no force being applied on this member. That's 0 newtons. And when it's neither tension nor compression, that is a special case where they just write N for neutral. So dB is neutral with what also means that 0 newtons of force. There's no push, there's no pull. It's just hanging there. So interesting. That means if you wanted to save money, theoretically, you could remove this truss and be left with just this outer triangle to work with. You would get the same kinds of results, I'm pretty sure. I'll leave that as an exercise for the interested reader. Okay, so yeah, as I look at this, it makes sense that you could remove this truss member, DB, and it would not have any effect. Also, I suppose I should write it as BD instead of DB, just the way they do in chemistry class. They try to always have it in a certain order. All right, well, there's only one truss member left, AD. Go ahead and, like me, maybe do a dedicated drawing showing what's going on at point A and then figure out AD from there. So I'm going to pause it while you figure it out. Go think. Okay, I did zoom in a little bit on the drawing. Should have done that earlier. So I've just drawn point A. Off to its right is point B. To the right and up is point D, and I didn't complete the truss because I don't want to confuse the forces with the structural members for a moment. What I wanted to do is clarify for you what we already know about point A. We know that the ground through the pivot point is pushing upwards with a force of 71.4 newtons through point A. That is to cancel out most of the load of the 100 newtons being applied at point D. Okay, so now that I can zoom in a little bit more, here's the original problem, load of 100 newtons at point D. I simplified it as if it were a straight line as far as calculating the reaction forces. Here was the 71.4 newtons reaction force acting through the pivot point A. In addition, we went on, at least I did, hopefully you went with me, and figured out by analyzing point C first, that's just my style, that B was being pulled to the right, and therefore A is pulling B to the left. And by Newton's third law, for every action, there's an equal and opposite reaction. If A is pulling B to the left, then B is pulling A to the right. Just like on a tug of war, the two teams are pulling the opposite team towards themselves. And that is what I've sketched here. This is the force of B pulling A to the right with a magnitude of 35.8 newtons. This is the force of the ground pushing up through the pivot point at point A with a magnitude of 71.4 newtons. If you do your math correctly, then the angle formed by a right triangle using these two legs and connecting them head to tail, not tail to tail, the angle that you get should be identical to the angle of the physical truss that connects point A to point D. And so now, as you look at this, I hope it becomes obvious to the viewer that D must not be pulling up and to the right, because that would just be adding to the forces that are already pushing it up and pulling it to the right. So D's job in this situation must be to be pushing A away from it, down and to the left. So this is the force caused by member AD. And for the components to work out correctly, its horizontal component must be 35.8 newtons. Its vertical component must be 71.4 newtons. And I would close this out by powering up my calculator and calculating Pythagorean's theorem. Beep, 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 beep. And I get 79.9 newtons as the magnitude of the force of member AD. And by now, you should realize, well, D is pushing A away from it. A is pushing D away from it. So therefore, this must be under compression. It's being squeezed by A and D. And so the member itself is squeezing back, relying on its stiffness to exert the force at these two endpoints. I suspect I have now completely analyzed this truss structure. My claim is this is under compression. This is neutral. This one is under compression. Tension here, tension there. Notice that the length of the truss is not related to the magnitude of the force. It is under certain conditions, but here's an example where this is pulling to the left with 35.8 newtons, and this longer beam is pulling B to the right with a force of 35.8 newtons. Okay, so this is what I believe is the solution. And what I'll do is to close this out is show what the official solution is, and we'll see how I did. Here's the solution, and you can see that they're using purple for a neutral truss. Truss BD has 0 newtons. The others match my own calculations within my round-off error. So this was a successfully worked example of how to do it. Good luck.